It's recording now.
Awesome. Jerry, can I ask you for that? Thank you. Study set. Okay, so let's start with the very first one. I think Dr. Alexander told you guys to look up the heat of formation for these. So, or just kidding. That we don't even need that for. So, number one, how do we solve it? What equation do we need? Anybody?
Is it the Q equals ms delta T?
Q equals ms delta T. Yes, that's exactly it. So, what are we looking for? What variable are we missing from the information that we're given?
The Q.
The Q, right? So we're missing Q, but we have mass. So what do we have for mass?
The 36 grams.
36 grams, right? And then our specific heat?
0.40.
0.40 joules over grams times Kelvin, right? And then our delta T, that's going to be final temperature minus initial temperature, right? So I guess, does anybody want to give us what that change in temperature is going to be? So we can skip some steps.
22.
22 horses, pigs, cows, unicorns?
Degrees
Celsius.
Degrees Celsius, right? Uh-oh, something's wrong. We have Kelvin here and Celsius here. Does it matter? Do we need to convert anything?
Does it not matter because there's a change? It's a change in temperature.
Right. It doesn't matter, but that's not why. Anybody want to help her out? Why doesn't it matter? No?
Here,
I'll give you a
Sophia,
hint.
actually, in this instance, it does matter because since we need to have all units the same. So since our specific heat has a unit of Kelvin, we need to convert our Celsius into Kelvin. That way they can cancel out mathematically.
Well, yes, but also you don't need to because Kelvin and Celsius have the same magnitude, so you can technically just rewrite your specific heat as 0.40 joules over grams times degrees Celsius, and you could still do the math.
Yeah, actually, what I was gonna say is that's what Eve meant, like when she was talking about how it doesn't matter. I'm pretty sure she was meaning that in the sense that it's the same number.
Yeah, we're using
Yeah,
the same
like-
number. We just need to make the units cancel out, right? So we just need to rewrite our specific heat in terms of Celsius, and we can just replace Kelvin with Celsius again because they have the same magnitude. So whether you measure your specific heat in Kelvin or in Celsius, you're going to measure the same difference, basically, right? So then now we just plug it in, right? So Q is equal to 36 times 0.40, 36 grams, my bad, times 0.40 joules over grams times degrees Celsius times 22 degrees Celsius. So then all of our units cancel out. And what should I get for Q?
$316.8.
0.8 cows, pigs, horses, unicorns?
Joules.
Kilojoules. Kilojoules.
Joules. This is kilojoules?
I think so.
No, just joules.
Okay. It's just joules? I'm not sure. I didn't do the math. Okay. Just joules. I'll take your word for it. If we wanted it in kilojoules, what would we need to do?
Is it divide by 1 times 10 to the third?
Divide by, yeah, 1 times 10 to the third or 1,000, right? Because dimension analysis, right? 1 kilojoule is 1,000 joules. And so then that would give you 0.3168 kilojoules, right? Okay, cool. Any questions on the first one?
No.
We're good? Okay, cool. So let's move on to the second one. What is the mathematical expression for the first law of thermodynamics? Anybody?
Is it the change in U is equal to Q plus W?
Q plus W. Yes. So what is Q? Heat, right? And then what is W? Work. Yes. So your change in, or your overall thermodynamic change of your system is going to be your heat plus your work. Yes? And then we know both of those equations. We knew Q, which we just used in the last problem. And then does anybody remember the formula for work? This is module.
How come it's Q plus W, not Q minus W?
I thought it was Q plus W.
It is Q plus W. The only time that you'll see one with a negative is if you're making them equal to each other. So it would be Q equals negative W, or W equals negative Q.
Okay, thanks.
Alrighty, and then I have in the chat work equals negative pressure times delta V, which is change in volume, right? So if you're asked to find delta U and you have everything that you need to solve for Q and solve for W, you should be able to solve for this equation, right? Cool. Any questions on the first law of thermodynamics? No? Okay, cool.
No.
So then the next two are, oh, does somebody have a question? Totally stop me if I skip over your question. No, we're good? Okay, cool. So the next two questions are vocabulary. So anybody want to give me the answer for number 3? So it's the function enthalpy, okay. And what is the variable that we use for enthalpy?
Delta H.
Delta H, right? So if you're asked for this vocabulary question, or if it asks you to define enthalpy or delta H, this is the definition that you would give, right? And what about number 4?
Delta U?
Delta U, okay, and what does delta U stand for? Or where did we get delta U from? Hint, hint. We literally just used it. No, that's okay. It's from the first law of thermodynamics, right? Yeah, it's a change in energy, but it's from we get it from the first law of thermodynamics. That's where that came from. Okay, so next thing is standard states. So what is a standard state before we get into determining them?
Whether it's like a solid, a liquid, or a gas?
Yeah, so a standard state is basically how you would normally find something on Earth, right? So in our case, we have we have usually more than 3 options, but you guys aren't there yet, so we have 3 options: solid, liquid, or gas, right? So water, how do we usually find water? Liquid. What about carbon dioxide? That's an L, by the way. So I heard solid for carbon dioxide.
Gas.
It's a gas.
Gas, right? Think about Remember, you breathe in oxygen, you breathe out carbon dioxide, right? What about sodium chloride?
Solid.
Solid, right? That's salt. What about copper?
Solid.
Solid, right? What about oxygen?
Gas.
And mercury?
Liquid.
Liquid, right? So I had some of my students ask, what if you don't, because for the most part, you'll be asked about things that you know, right? So I had some students ask, what if you don't know what it is, right? My best advice is take your best guess. For the periodic table, for the most part, everything on the rightmost side, so like noble gases, haha, guess what they are, and halogens are gases, and then metals are for the most part solid except for mercury, right? And the metalloids, for the most part, are solid, I think.
Can I put some input in here?
Yes, 100%, go for it.
All right. So, like she was saying, like what Sophia was saying earlier, most of the nonmetals are gases, and after that, everything else is a solid except for iodine, bromine, and I think gallium. Iodine's a solid, gallium and bromine are liquids, which are the symbols that she's writing there.
So these are the exceptions. Oh, that was bad. I'm sorry. I didn't mean to do that.
That's not including mercury, which you already know, though. So
Yeah, and then mercury, we just said was a liquid, right? Okay, any questions on this? No? Okay, cool. So now let's write the reaction for the enthalpy of formation of sodium chloride. So let's start with, I guess, the easy part. What would be the formula for sodium chloride? NaCl, right? And then if we want the formula for the enthalpy of formation of sodium chloride, is there anything special that we need to keep in mind when we're writing our equation? Specifically about how much product you're making?
Wait, what do you mean?
Ratio, okay. Okay, so you can have enthalpy of formation for your balanced equation, right? But then there's a special type of enthalpy of formation, which is called the standard enthalpy of formation. And there's something special about that formula. Does anybody remember what it is? Specifically about how much product you're making?
well, didn't he already say that it's 1 mole of it?
Oh, somebody said it?
Yeah.
Oh, sorry, my Wi-Fi is lagging, I'm sorry. Yes, so you're going to make 1 mole of product, right? So when we're balancing this equation, we want to make sure that we only make 1 mole of product. Anyway, so let's backtrack. We have sodium chloride, so what do we need to make sodium chloride on our reactant side? Sodium and chloride, right? So chlorine is special because, chlorine is special. What's special about it? I think that's a better question.
Isn't it that it doesn't like to be by itself?
Yeah, it doesn't like to be by itself, also known as diatomic, right? So we need a subscript of 2 here, right? So now our equation is off balance, right? It's unbalanced, but we still want to keep 1 mole of product. So what should we do to our coefficients on our reactant side? David says times 2.
Times 1/2.
Georgina
So it
says
can be
times
1.
1/2. Yeah, 1/2, right? Because we're trying to keep 1 mole of product. So if we do 2, we're going to end up with 4 chlorines on the reactant side, which is going to throw off our products even more. So 1/2 is better because then you only have, technically, right, 1 chlorine to make sodium chloride. Does that make sense to everybody? Any questions?
keep in mind that this is specifically for the standard enthalpy of formation, meaning we're just looking for 1 mole of product specifically. So there's not like by any means a perfectly balanced equation, meaning that we're not looking at the full reaction. We're just looking for 1 mole of a product using its base elements that we can find.
Yeah, exactly. So usually we would want to stick to only whole numbers, right? But when it comes to the standard enthalpy of formation, it's okay for us to use fractions because we want only 1 mole of product. Okay, so I'm gonna clear all the notes left. Does anybody need them before I do? Speak now or forever hold your peace. Okay. 3, 2, 1. Hope you didn't need it because it's gone. Okay. So then I think this is the last question, right? Alrighty. Would you mind zooming in, Jerry? My eyes, they are bad. Thanks. Okay. So last question says, one of the compounds found in gasoline is heptane, C7H16. Write a balanced chemical equation for the combustion of heptane. So combustion reactions, kind of easy, or actually super easy because you always end up with the same 2 products, right? So what are the same 2 products you always get from a combustion reaction? Water and carbon dioxide, right? Okay, and then we know for sure one of our reactants is going to be C7H16, right? So what is this going to react with to make a combustion reaction? Oxygen gas, right? Okay, so now is this equation balanced? No, right? So we need to balance it. So do you guys want to go over balancing it together or do you guys want to try it for yourselves? If you feel brave and you think you've got it, just shout out or type in the coefficients in the chat.
I got 11 for where oxygen is,
Okay,
and then I got 7 where carbon dioxide is, and then
Okay.
I got 8 in the water.
okay. Does everybody agree? Anybody disagree? Ready? Georgina agrees. I hear no dissent, so I agree too. So I think we're good. Alrighty, so now we're going to compute the standard enthalpy of change for combustion of 1 mole of heptane. So I think for this one, Dr. Alexander told you guys to look up those heat of formations, right? So, but one of these we don't even have to look up. Which ones don't we have to look up?
Is it the ones that are by themselves?
Okay, so which ones would those be?
Oxygen?
Oxygen, right? Does anybody have a better reason for why oxygen has an heat of formation of 0? Do you have to make oxygen gas or do you just kind of find it like that already? Yeah, you find it like that, right? It's a diatomic element. So if you were to just like go on a scavenger hunt looking for oxygen gas, you're always going to find oxygen gas in a pair, right? So you don't have to make it. You're always going to find it like that. The other compounds, however, you can't, I mean, you can find them, but they're going to be made, right? The reactions between 2 different substances, right? So would anybody like to be so kind as to tell me the heat of formations for heptane, water, and or carbon dioxide?
To be
Do
more
we have
specific, to be more
Sorry.
specific when you're looking for them, for heptane, look for it in liquid form, water in vapor form, so gaseous form, and carbon dioxide in gaseous form.
Do we have to
think,
look it up? Or are we meant to know them?
No,
on the
for-
exam, he'll give them to you.
Oh,
But-
okay.
But in this
Yeah.
instance, you got to look it up. It wasn't
I can-
provided.
I can give you the one for water and carbon dioxide right now, actually,
Bet.
because I feel that'd be simpler. For water, it's negative 241.8. And then for carbon
Is it
dioxide, it's
kilojoules or joules?
kilojoules per mole.
Okay.
And then for carbon dioxide, it's negative 393.5 kilojoules per mole.
I got heptane for you, Sophia. So heptane's gonna be
Oh,
heptane.
yeah.
Oh, oh, perfect. Wait, did they
They
put that
found
already?
it. I
Oh,
just
okay.
didn't catch it. Negative 187.6
Yep.
kilojoules per mole. Okay, so this is Hess's law. Is this direct method Hess's law or indirect method Hess's law?
Direct.
Direct method, right? So what equation do we need to use? Anybody?
Is it when we have the products minus the reactants?
Yeah, so it's gonna be heat of formation of the reaction, right? Is going to equal the summation times of the moles of the products, or the, sorry, heat of formation of the products minus the summation of the moles of the heat of formation. I'm pretty sure I'm reading this wrong, but you guys get the gist, right? That's what that looks like. Okay, so what do we have and what are we looking for? We have products and reactants, okay, and we're looking for a change in H of the reaction, right? Okay, cool. So then I'm gonna, for the sake of space, okay, and time, I'm just gonna put the equal sign, but we're still solving for this part, okay? So I'm just gonna put the equal sign. So then, what should I write on the right side of the equation?
You need to write minus 241.8.
Minus 241.8, okay.
Oh, but before that, you need to multiply by 8 because
Okay, because we have 8 moles, right? Okay. Plus,
and then 7 times negative 393.5.
okay, that's not how you spell kilojoules. Okay, and then we have minus 11 times 0, right? That one's easy. Plus, you totally just not write that out, but I just like felt like it. What's the last part I need to write?
Plus negative 187.6.
Yeah, plus negative 187.6 kilojoules. Yay. Okay, kilojoules per mole, right? And then if you're handy with your math, right, this just turns into a minus sign. Okay, so then if you plug this into your calculator, what should you get as your heat of formation for the reaction? Anybody? Anybody there?
Is it
Negative
4.82
uh-huh.
times 10 to the third?
And this is kilojoules per mole, right? Okay, I got 2 people with the same answer. Anybody disagree?
I have a question.
Yes.
Did you guys add or subtract the 187.6?
Oh yeah. Because then look, it's a minus minus a minus, so it turns into a plus.
It's because that's a common mistake that people make. So it's double checking.
I didn't do the math, so I have absolutely no idea. You guys did the math. What did you do?
You add it because how she said it, it's a negative, a double negative, so it turns into a positive.
To a positive, right? Cool. So that's the end of study set number 9. Any questions on any of these? No? Okay, cool. Who wants to take over?
Yeah, I'll take over. So, Jeremiah, you can stop sharing. I have the file with me. All right, so next up is study question set number 10. So, making sure I'm not pulling up the wrong one. Perfect. So, we're still dealing with enthalpy of formation, but we're just gonna get more into it right now. So, let's start off with the first one here, where we have the chemical equation of decomposition of hydrogen peroxide is as follows, and it's asking us to determine the state of enthalpy or enthalpy change, or delta H, little degree sign, for the decomposition per 1 mole of hydrogen peroxide. So for, I guess, number 2, technically, give a brief description on how refrigeration works. So who can tell me how, like, I guess this would work out? Seen as, let me quickly check. So what is the enthalpy of change of formation for hydrogen peroxide? What is that equal to? In this case, this is something that Dr. Alexander wants you to look up, so it's not given right off the bat. Let's see. So who can tell me what is the enthalpy of formation for hydrogen peroxide here? Let's see. Negative 187.62. Anyone agree or disagree? All right, so we have negative 187.6. It's typically going to be kilojoules per mole. So we see here that it's so we see it's a negative number. So kind of a follow-up to what's going on, given a brief explanation of how refrigeration works. If we see here, since this is a negative number, is this exothermic or endothermic? This reaction that we see here, the decomposition. Exactly, it's exothermic. Since the system is negative, it's losing energy, so it's releasing that energy. Yeah, so it's exothermic, meaning you're gonna feel heat coming off it. So if you feel heat coming off of something that's releasing it, then you would feel it getting colder by absorbing energy, being the other way around, being endothermic. So going into how, give a brief description of how refrigeration works, who can give me an idea on how that works, how refrigerations work? Yeah, yes, the right way.
Well, how do things get cold? I guess would probably be a good startup question.
Yeah.
I think for the question 1, don't we have to work out the enthalpy change for the equation?
It wasn't really given. I believe. So I think it was something you just had to look up. Because, you know, since you will be provided them on the exam.
Yeah, but do we not have to do the enthalpy formation of water?
Yeah.
Minus,
Sorry, go ahead.
like, and then minus it from the enthalpy formation of the hydrogen peroxide. Like,
Yeah,
if you times by one.
sorry if I kept interrupting you, sorry. But yeah, you are correct. It's just that how Dr. Alexander just kind of said, you just look it up and then solve it that way. To like, for the sake of time, trying to go through it, since you guys did really, you know, really good on doing it in the previous one. Because this is for the sake of time and trying to go through it. But just to like double check our answer, let's just do that real quick. So we would need the enthalpy change of formation of water, as well as the change in enthalpy of formation for hydrogen peroxide here. So
I think that's what he gave.
oh, did he? Oh,
Yeah.
I see. Okay, so let me fix this real quick. So if we were to solve for, you know, of the whole reaction, the change in enthalpy of formation. So we have standard change in enthalpy of formation of our reaction, like you said. So the products minus reactants. In this case, since this is 0, like we said earlier, because since it's self-bonding, you can only find it as a diatomic element. So for water, what was the enthalpy of formation for water? Since we know the one for hydrogen peroxide.
It was negative 218.8.
Negative 218.8. And I'm just trying to find, oh, negative 241.8. So roughly around there. Hold on, I'm just trying to scroll through chat, find the for hydrogen peroxide. There we go. So this here was negative 187.6. So let's see. Negative 241.8. So so the one that Onesimo gave, check to see what state of matter that's in, because here we're working with liquid hydrogen peroxide. So here,
I think that's for water.
Oh, was it?
Yeah, because that's the one I gave for water last time too.
Okay. I see. So negative 241.8. So obviously with a double negative, they cancel each other out. So you're adding up this negative plus this positive. And what will we get in the end as our enthalpy of change of formation for our reaction? We have negative 241.8 plus positive 187.6. Here, this is all kilojoules per mole. Let's see here. Let's see, we have negative 98.2 kilojoules per mole. Does anyone disagree or they agree about what Juan Andres got? Let's see, I'll take that silence as a no, so everyone agrees. So we have negative 9. Oh, sorry, go ahead.
So we put in the calculator minus 241.8 plus 187.6.
Exactly, yes.
I got minus 54.
Let's see, so we have negative 241.8 plus 187.6.
So I just looked it up right now. So the delta H for water is incorrect.
Was it?
I looked it up and I got negative 286. So when you do negative 286 plus 187.6, you get 98.4, which is roughly around negative 98.2.
So that, but also I forgot something very crucial. So remember that we need to represent the energy by the number of moles within the reaction. So I'm just gonna put delta H RxN. Since we have 2 moles of peroxide, we must multiply it by 2. So our energy by times 2. And since we have 2 moles of water, we also need to multiply this by 2 as well. That was something I forgot. So, and also, can you repeat what you got for the enthalpy of formation for water? You said it was 268?
It was negative 286.
Negative 286. All right. So remember to don't do the mistake that I did by not multiplying it by the number of moles representing our reaction. So if we do that, B2 times negative 286.6, I mean 0.8. Let's see here. Let's see, then plus 2 times 187.6. Let's see. Oh, remember to make keep this negative.
My calculator.
Let's see. Yeah, so like do double check your like calculators and stuff. Negative 196. Let's see. It should come out to negative 98.2. Let's see what's going on here. So we have 2. Let's see what's going on with all our calculators. Maybe. Let's see.
I got negative 108.4.
Let's see, Jeremiah, are you getting something similar like this, or?
I got negative 198.4.
So we get roughly around this range. Negative 198.4. So
Alan, I have somebody saying that the heat of formation of H2O2 is 191.2. I don't know if that changes things.
191. It shouldn't by much, but yeah, I just don't know why he didn't give Dr. Alexander didn't give it to you, because a lot of people are getting different things.
It's because why are we using 187.6? Because that one is we use that one for heptane, but
oh, did we? Okay, because I was looking. My bad. Yeah, because I asked what was the enthalpy formation for hydrogen peroxide, and I saw that that was placed in the chat, most recent. So I guess that could explain it. Yes, that would explain it. All right, yeah, because a lot of things are not given, and this was supposed to be that. All right. So who does have the enthalpy of formation for liquid hydrogen peroxide here?
They got 191.2.
Yeah,
I don't know if it's positive or negative though.
I see it as negative in the chat. So that I see 190. I see 196, 191 around that range. 196.8. So it's negative, but then since it's being subtracted, it's gonna be a positive. So now that we plug this into our calculator.
No, Alan,
Yeah,
I think that's for something else.
Is it? Oh my God.
I'm pretty sure.
On Google says negative 190.1.
Then go with that.
We'll go with that then. Oh my God. 0.1. So if we put this into our calculator, hopefully, let's see here. Yeah, we should end up with around the range of negative 193.4 kilojoules per mole. Does everyone agree? Anyone disagree? Because, oh my God, sorry, it's just, anyone got something similar around this range?
So the answer that the professor gave us in the study guide is wrong?
It might be like, I wouldn't say that it isn't, but it's just I don't know which specific values he's basing it off. I'm seeing as everyone keep giving different values. So we got.
Yeah, so right now there's a big chance that we get things wrong because we're basically doing our best guess as to what heat of formation Dr. Alexander wants us to use. But on the exam, you'll be given exactly what he wants. So as long as you know how to use your equation and you trust your algebra, you should be fine.
Let's see, divide by 2. No, we wouldn't divide by 2. We would have to multiply by 2, because since we have 2 moles of our hydrogen peroxide, we need to represent this by we need to multiply the energy by 2. Same thing with the water. So let's see. Let's move forward because like just what's important is that you know the process, not the exact values for sure, because those you will have to be given. So let's move on to here, number 2, where a brief description of refrigeration. So how does stuff get cold? Can anyone give it an idea of how this works? Let's see. Oh, there we go. So heat gets drawn out of the refrigerator. So how does the heat get drawn out specifically? So we know that heat gets drawn out. But like, can anyone be more specific on how or why does that? Exactly. So by increasing the pressure, what happens? So whenever you're increasing pressure, sorry, just trying to look back at it here. So pressure is involved in it. So you would increase pressure. So it's going to put increase pressure. Let's see, because you have a compressor, right? So you got to compress a gas. Let's see here. Can anyone elaborate on that? So we increase the pressure on it, but anything else? So let's see. Yeah, perfect. So when we increase pressure, right, temperature increases, right? So when we increase, so remember the gas laws where whenever pressure increases, so does your temperature. So by following that, we would take that to then, because here's the compressor, right? So then we would then take it to the, I believe, what was it called? The evaporator, right? So when we increase the pressure, we are increasing the temperature. And like Onesimo was saying, where heat flows from hot to cold, we would take it to another area where it would then become endothermic. And when something's endothermic, it's absorbing that heat, making it colder. So whenever, say, you go outside and then like it's colder, so you would start feeling yourself get. Let me give a bit of explanation. So say you put your hand in the refrigerator, right? So it's starting to get colder, right? That's because the surrounding air is colder than your hand, so that energy has to go to it. So like Onesimo said, into the evaporator. So we increase the pressure, so it's like a little container. I don't know how it actually looks like, but here we have our gas. So when we increase the pressure, it increases the temperature along with it. So let's see here. Yeah, the pressure decreases and becomes colder, and then the space inside the refrigerator. So much like what Nestor was saying, is how does refrigeration look? So we're taking an exothermic process and then taking it to an endothermic to an endothermic process. So it makes things colder than whatever's outside of the refrigerator. Does that make sense? Is anyone confused by that? Because a lot of it, just to get the basics, is like exothermic and then endothermic. Let's see. So let's move on real quick, actually, since just we need to get through this review. So right here, where it says give the characteristics of a good refrigerant. So what would be a good refrigerator characteristics that we would want here? can tell me? Any ideas? Yeah, so pressure is another thing. So one thing we do want is good pressure, right? So we want good pressure, because if we don't have anything that can give enough pressure, it's not going to be able to compress and then decompress in order to make it the exothermic and endothermic process, right? So that's one of them. But what's another thing, right? Because here's this gas, right? So if the gas is what's being compressed and decompressed, let's see here. Exactly, a gas that can be liquefied with pressure. So if we were to take something like air is very hard to make liquid, even with like high amounts of pressure. It's very difficult to make it into a liquid, right? So this is a good pressure and a liquid that's easily not a liquid, a gas that's easily compressed into a liquid. Because if it takes too much pressure for a gas to become liquid, it's not going to be good as a refrigerant, meaning, it's going to take more energy to make it hotter and then colder for the refrigerator to work. So a gas easily liquefiable. It's going to call that. So mainly this is the main reason we would want within a good refrigerator, a good refrigerant, along with a good pressure, in order to actually put pressure into the gas to liquefy it and then decompress it back into a liquid. So let's move on here to number 4, something that we'll be more comfortable with. So the reaction of sulfuric acid with sodium carbonate in an aqueous solution is shown in this reaction, where we have here sulfuric acid, sodium carbonate, making sodium sulfate, liquid water, and carbon dioxide gas. So assume that the reaction is carried out under standard thermodynamic conditions. And it's asking us to compute the amount of pressure, volume, work that is done by the system onto the surroundings when 1 mole of sulfuric acid reacts with 1 mole of sodium bicarbonate. So right now it's asking us to determine the amount of energy by this work, or the amount of work by 1 mole. So who has an idea of how we can get this done given the problem we're given, like how it's worded? So really quick, so looking back at the problem, what does the problem give us specifically? Like what information does it give us? Let's see, standard conditions. Yeah, so it says standard conditions. So that's going to, since we're working under standard conditions, what are standard conditions for thermodynamics? Because it's different from your STP, which is specific for gases. So we have standard thermodynamic conditions. So what is being standardized here? Let's see here. So we hear a pressure and a temperature. So we have temperature for standard thermodynamics condition is equal to 298 Kelvin, where pressure is 1 atmosphere. So we have 2 values already there. And right here, it's asking us to look for the amount of pressure, volume, and work. So, well, not pressure, but mainly, pressure, volume. So it's your liters, atmospheres. So, or atmosphere liters. So liters times atmospheres, ATM. So we're looking for work. So what will be the formula in order to look for work? What does work equal to?
Well, work is minus P and then delta V.
So negative pressure times change in volume, right? So we see that we are working here under a standard, let's see here, just looking through it real quick. Yeah, okay. So we do have a pressure already, but we don't necessarily have a, well, let me see, reading here. We don't necessarily have a change of volume just yet here. So let's see here. Here, Jeremiah, can you help me out here while I'm trying to look through here because I feel like I'm missing something.
Yeah, well, there's two more things. So it says that compute the amount of pressure volume work that is done by the system on the surroundings. So from that, is your work going to be positive or negative?
Negative?
Negative, right? And then the one last thing is that it says when 1 mole of sulfuric acid reacts with 1 mole of sodium carbonate. So with that, you should be able to figure out the volume with that, because you'll have your pressure, you'll have your N, you'll have your constant, and you'll have your temperature.
So yeah, in this case, well, we would have PV equals nRT, but specifically, let's see. Here, Jeremiah, correct me if I'm wrong here, because Dr. Alexander set this out pretty weirdly. We would have to specifically look for it into the carbon dioxide since that's the only gas we have, right?
Yeah, you'd find the volume of carbon dioxide. Or moles, sorry.
Yeah. So we would have to find the moles of carbon dioxide first of all, if we want to find a change of volume beforehand. So how can I, since I'm given 1 mole of each substance, how many moles of carbon dioxide would I have? Let's see. So exactly, Gabriel. So you would have 1 mole since we're working with 1 mole of each reactant already, then everything is already going to be 1-to-1. So we have 1 mole of carbon dioxide being produced already. So if that's the case, we know we have our N, which is 1, R, which is our gas constant. And then we also have our pressure, P, since we're working with standard thermodynamic. I mean, we also have temperature here, 298 K. And since it's working under standard thermodynamic conditions, we have 1 atm of pressure. So let me quickly make some room here. So we write this out into our equation. So, well, first of all, let's isolate V since that's what we're looking for, right? So we have PV equals nRT. How can I isolate my V here? Since that's what I'm looking for.
Dividing nRT by P.
So if we divide P on both sides, we end up with V equals to nRT over P. Now that we've isolated the value we're looking for, let's now plug in the values that we know we have. So we have V is equal to, we know we have 1 mole times our gas constant. And who remembers what that gas constant is? Let's see here. Exactly, 0.0821. And remember, it's going to be liter atmospheres per mole Kelvin.
Do we have to remember that for the exam?
Yeah, so for your constants, you are going to have to memorize them since they are constants, okay. Yes. But in the event that you forget them and you try to look them up, be careful because there are multiple different R constants. So you might accidentally find one like kilojoules per mole Celsius or something like that. So be careful. Make sure it's this gas constant, liter atmospheres per mole Kelvin. And then we multiply it by our Kelvin, 298 K all divided by our pressure, which is...
This exam's in Lockdown Browser, right?
Mm-hmm.
Okay, thanks.
Here. So here, really quick, just to save time, we can cancel out the units that... Oops, let me undo that. We cancel out the units that we can cancel at the moment. And now we're left with liters, which is perfect since we have a volume here. So our volume is equal to what? Now that we've solved for this operation, who can tell me? Let's see here. Yeah, perfect. 24.5 liters. So let's see here. It's 24.5 liters. So in that range, right? So now that we have a volume here, well, we have a volume. We don't necessarily know it's the change of volume, right? But if we look,
Actually,
is it actually the change of volume?
yeah. So that will actually be the change of volume because what's happening is this chemical equation is showing us what's happening. Like since that's the product, that's how much is coming out from before the equation occurs. So this is the end product, which will be its change.
Well, yes, technically it is the change of volume. I see what you mean, Jeremiah, but like, because what I mean is this has to be negative, because remember that we were looking for, it was carbon dioxide gas, right? But initially we didn't have carbon dioxide gas, so technically that's a volume of 0, right? So our initial volume. But
yeah.
Oh wait, am I?
The change of volume will be positive.
It'll be positive. Never mind. Okay, I was thinking it the other way around. So yes, so it'll still be the same because if we had an initial volume of 0 for that carbon dioxide, and then we had a final volume. So remember, it's final minus initial of this 24.5 liters. This is now going to be our change in volume. So let me clean this up now that we have a space. So now we have delta V is equal to 24.5. So now that we have values for our pressure and our change in volume, now we can plug it into our work. So we have work is equal to -1 atm times 24.5 liters. So what would my work now equal to? This is before, converting to anything. Let's see. All right. So I would multiply these two. So what would my answer be, and what would my new units be?
It would be negative 24.5 liters times ATM.
Perfect. Liters times ATM, since it's asking for the amount of that's technically pressure volume work, because he likes to word it out that way. So this would be one of our answers right now for this. Well, for number 1 technically. So work is equal to negative 24.5 liter atmospheres. But remember, work is also energy, because here at the bottom, this next follow-up question, where it's determined the amount of energy required to accomplish this work. So we know that our work is negative 24.5 liter atmospheres. So how can I convert this work into a unit of energy, which is, say, for example, joules? Let's see here. Perfect. We would multiply by 101.325. And remember, it's because the conversion. So for every, let me clean this up real quick right here. Remember your conversion factor, where for every 101.325 joules, there's every 1 liter atmosphere. So if these two equal each other, then we can convert between the two. So if we do that, multiplied by 101.325 joules over 1 liter atmosphere. Our liter atmospheres cancel out, so we multiply by the top and divide by the bottom now. So how much energy am I giving off from this work? Perfect. Let's see, we have negative 2,482.46 joules. Does everyone agree? Anyone disagree? Let's see, I'll take that silence as you guys agree. So yeah, so this would be your answer for the follow-up part. So the amount of energy from the work accomplished is negative 2,482.42 joules, which makes sense, right? Since our work is negative, the amount of energy is also negative, meaning it's releasing it into the surroundings. Perfect. So if you guys have any questions or feel confused or lost at any point, feel free to interrupt me. Or if you feel like I'm talking too fast, it's okay to interrupt me. But let's move on here to number 5, where we see that it mentions, so the 4-stroke internal combustion engine is an example of a device that accomplishes a large amount of pressure volume work in one of the 4 strokes. List the names of the 4 strokes and describe what happens in the stroke in which large amount in pressure volume works. So essentially, we're just listing the 4 strokes that happen and describe what happens when that one stroke has the large amount of work, basically the large amount of work, which is in liters atmosphere, so pressure volume work. So who can give me the names of one of the strokes or the first stroke? So there are 4 strokes. Who can tell me what the first one is? Oh, let's see. Intake. So the first one is the intake. And what would be the second one?
Compression.
Perfect. Compression, because first you got to take in air and then you got to compress it. And what would be the third one?
Combustion.
We have combustion. So we intake air, we compress it, and then we combust it, basically have it react and explode, quote unquote. And then we have our last stroke, and what would that be? Let's see here. Exhaust. Yeah, exactly. We release that air. So we exhaust the air that's left from the reaction. So we exhaust it out. Let me fix that. Perfect. So you intake the air, you compress it until it combusts, and then it exhausts your products out. Perfect. So which of these strokes has the largest or the large pressure increase or your large amount of work happening? So it's in the combustion. This is where you have the large amount of pressure volume work. And why is the combustion having the large amount of pressure volume work? Like, who can tell me why combustion has such large amounts of work happening? Let's see. Yeah, exactly, Anasimo. So perfect. Because of all the heat and pressure, because remember combustion, if you remember combustion reaction, it releases energy. So like when you light a match or whenever the pistons are going off in your car, it's letting off heat. So this will be the only one that's releasing that large amount of quote unquote heat or work happening. Perfect, exactly. So going on to the last one for this, for study question number 10. So we have number 6. So the crystal structure of sodium chloride is very stable, yet the salt is very soluble in water. So why is that the case? Why is it very soluble in water even though the solid structure is very stable? Yeah, so the water does break up a bonds. That is a part of it. But why specifically? Like, what is it that makes it water super easy? Perfect, yeah, because of its large lattice energy, the larger lattice energy. See, with the hydrogen share an electron with the chlorine. Oh, there. Yeah, so you figure, okay, you figured it out, yeah. Yeah, since water, let me quickly, since H2O has a larger lattice energy, I'm just gonna put lattice E for short, than say your sodium chloride, not sodium, yeah, sodium chloride, then it'll be much easier for it to break up those bonds when dissolved into water. So that's the last question for your study question set 10. I know we kind of had a bit of a confusion at the start, but is anyone confused about any of these other questions or any concerns regarding enthalpy or some of the concepts here?
Wait, Alan, for
Yeah.
that last one, what did you say was the answer?
Oh, that since water has a larger lattice energy, then sodium
Oh,
chloride is
okay.
able to break it up. Yeah.
Yeah.
So let's see. Any questions before we move on? No. All right. So let's see. Here. Jeremiah, do you want to take over for the 11th? Yeah.
Yeah, I got 11.
All right. Perfect.
All right. So for some strange reason, Dr. Alexander loves giving you guys standard enthalpies without any enthalpies. So for these two, the ones that I got, or I guess, well, we'll use, is for iron. It's going to be negative 822.2 kilojoules per mole. And then for aluminum, we'll be using negative 1,669.8 kilojoules per mole. So with these enthalpies given, what would be our standard enthalpy for the reaction? Oh, there we go. Yeah, negative 845.6. For this one, it was pretty straightforward since there were no moles that you needed to use. Since iron and aluminum were both 0. So all you needed to do was add the negative 827 or 822.2 to the negative 1,669.8. Make sense? Cool. So for the list of subshells for the first electron shells, what it's asking here is the subshells for basically the first 4 rows. So for the first row, what would it be?
One S.
Just one S, right? Because all that's on the first row is hydrogen and helium. And those two will make up that one S subshell. What about for the second row?
2s and 2p.
2s and 2p, right? This time it goes all the way to neon, and neon's in the p subshell, which is L equals 1. So what about for the third row? Well, which two for sure should be there?
3s and 3p and 3d.
Okay, and 3D. So the reason that 3D is here, even though it's on the fourth row, we know that for its energy level that it starts in the third one. And the way that we are taught this is by subtracting 1 from the first row that it's on. So if it's in the fourth row, it's going to be in the third. If it's in the fifth row, it's going to be in the fourth, etc., etc. Now, what about for the fourth energy level or fourth row?
For S, for P, for D, and for F.
Right, for S, for P, for D, and for F. So just like with the D subshell, the F subshell, you also subtract, but for them, you'll subtract 2. So for them, they're on the 6th and the 7th row, but the way that we'll actually see it is that they're on the 4th and the 5th row. Any questions on these subshells?
No.
All right, so the next question, it asks how many orbitals are located. Now, for the first one, for the S, how many electrons can it hold?
2.
2, right? And how many orbitals does the S one have?
1.
Yeah, it should for sure have 1, right? So the S has one orbital, and it has 2 columns or 2 electrons. So with this in mind, what about the p orbital or p subshell? Sorry.
Is it 3?
It's 3, right? So for the p subshell, it has 6 columns, 6 divided by 2, because each orbital will have 2 electrons. There will be 3 orbitals. So we know S, we know P. What about D?
It holds 10 electrons, so it would be 5 orbitals.
Perfect. Uh-huh. 5. And then last but not least, F.
7, because it has 14. It holds 14 electrons.
Perfect. Yep. So, well, you guys, since we were able to answer 3 pretty easily, what do you guys think is the answer for number 4?
Is it 2?
Yeah, it's 2. Honestly, I kind of feel like this one should have been put before number 3, but we got through it. So, number 5, what is the maximum number of electrons that can occupy each of the following types of subshells? We kind of already said that one too, but just as a recap, for S, what would it be? Electrons this time.
2.
Okay, and then P? Beautiful. And last but not least, F.
14.
On fire. Couldn't have said it better myself. So, what is the maximum number of electrons that can occupy each of the first 4 shells? So the way we're going to do this, remember back how we listed all the subshells for the first 4 electron shells? The way that we're going to do this now is these numbers that we came up for each of these subshells, we're going to replace for these letters. So for S, instead of S, we'll put 2. Instead of P, we'll put 6, so on and so forth. So for the first shell, what will it be? For the first one, it just has the S subshell. So how many electrons can it have?
Two.
2, right? And then for the second one, it has a S and a P. So how many electrons can it have now?
8.
8, okay. And then for the third,
$18.
18, okay. And then last but not least, I don't know why it keeps disappearing, but that's supposed to be 18. And then last but not least for the fourth,
18 plus 12.
18 plus 12, okay, which is? Or what's 28 plus 2?
30.
30, perfect. So we got 30, we have 18, 8, and 2. And that's how the news goes. That's it for 6. So for number 7, what are the allowable values? Well, for n, how do we figure out what n is in the first place? What on the periodic table tells us what n is?
The
I'm
period.
sorry? Right, the periods or the rows. So how many periods are there on the periodic table?
7.
7, okay, so that's the highest we can go. Can we have a 0 period?
No.
Okay, so what's the lowest it can go to?
1.
1. So 1 through 7, or you can write it out. I prefer using ranges. Now, so that's our answer for 7, 1 through 7. Anyways, so number 8, what are the allowable values of the angular momentum quantum number L for n equals 3? So for L, how are we able to figure out based off of what n is?
Isn't it n minus 1?
Perfect, n minus 1, right? So if n's 3, what's the highest our angular momentum can be?
Two.
Okay, and what's the lowest? Can we have a 0 for L?
Yes.
Well, there you go. So it'll be from 0 to 2. Any questions on the quantum numbers for n and L? Make sense? Cool. So what are the allowable values of a magnetic quantum number m sub L for L equals 2? Now for m sub L, how does that relate to what L is? How do we use L to find m sub L? Okay, well, if L equals 2, what's at least one of the numbers that m sub L can be?
Two.
2, right? Okay, so it for sure can be 2. Can it be 1?
Yeah.
Okay. What else can it be?
0, -1, -2.
0, -1, and -2. So how did you come up with -2, -1, 0, 1, and 2?
It's between -2 and 2.
Okay, which is negative L to L, right? So, oh, did you have a question?
Sorry, I have a question for number 8.
Okay, what's up?
I was just wondering, why is it 0 to 2 and it's not just 2?
So for 8, it's asking what are the allowable values. So basically, the way that we see it is that L needs to be less than N. So it can't be N for sure. And since we're using whole numbers, that's why the highest it can be is N minus 1.
Okay, thank you.
Of course, you will only have a single number for each of these if you're doing it based off of an element. But since it's asking for allowable values, we have ranges now. So for number 10, what are the values for N and L for a 4D subshell? Okay, well for N, excuse me, we're looking at the D subshell. What's up, Pizza?
Sorry, I meant to raise my hand, and I think that's waving. Anyways, I have a question. Like for 9,
Okay.
how do we find? Like, how do we know how to find MOL?
Right. So
I understand that it's like negative L to L. So would we just use? It's basically like using the same numbers as L, but then turning them negative and positive. You know?
Yes. Okay. Before I continue, have you guys practiced finding quantum numbers for certain elements? Or do you guys want to go over an example of that?
Let's do an example.
All right. So I just so happen to have a periodic table on my screen. So the way that I go about finding the quantum numbers for when looking at the periodic table is, like said earlier, N is the period or the row. Let me make sure I'm annotating. Wait, give me a second. There we go. Let's do that. We do it based off the period. That's for N. Now for L, for the periodic table, for the elements that are on the periodic table, what we typically use is from 0 to 3. Now, in order to figure out where on the periodic table we're looking, L is pretty important. So we have 0, we have 1 on the right side, we have 2, which is in the middle, and we have 3. Now, each of these numbers are assigned a certain subshell, like we were talking about earlier. 0 being S, 1 being P, 2 being D, and 3 being F. Now we're able to figure out N and L. Now for M sub L, the way that I do it, since we have a set amount of orbitals, and those orbitals can go from negative L to positive L, and there's double that amount of columns, the way that I look at it is, well, for the S, there's only one orbital, so they're both going to be 0 for M sub L. For P, since L is 1, it can go from negative 1 all the way to 1. So negative 1, 0, 1, and then negative 1, 0, 1. And for this, the reason why I do negative 1, 0, 1, and then repeat it again is because from Hund's rule, it says that we'll put an electron in each orbital before we start filling any sort of orbital. So there needs to be one in all three before we start filling them again. And then continuing forward, so it'll be negative 2, negative 1, 0, 1, 2, negative 2, negative 1, 0, 1, 2. And you guys, when you start using your periodic table on the test, you can write all over it or whatever, and that should be fine. And it will just help to be as a guide for you. That way you don't accidentally put like the wrong numbers or anything like that. 3, and then negative 3, negative 2, negative 1, 0, 1, 3. Oh, that's 2, sorry, 3. Now these elements right here, 71 and 103, lutetium and lawrencium, even though they are down here in the 3F, they're actually supposed to be seen as if they're right here in the actual D orbital. So these will be 5 and 6 on the negative 2 for M sub L in that D shell. But I wouldn't worry too much about that. And so that's how it is for N, L, M sub L. And now for M sub S, the way I do it, well, before we start filling up this, like pairing them, that's how we'll determine whether or not it's going to be a plus 1/2 or a negative 1/2. So the ones to the left of that half part will be plus 1/2, and the ones to the right of it will be negative 1/2. So, I mean, we've all have seen ions before. When we're looking on the left side of the periodic table, those are positive. When we're looking at the right side of the periodic table, those are negative, just as a rule of thumb. So now that we are able to situate ourselves, see how everything is, it's really easy to have some random numbers and tell what the quantum numbers are. So, Alan, if you could you give me some quantum numbers? Any at all?
Hello? Okay, my mic was acting for a moment. Okay. Do you want me to give you like actual possible quantum numbers, or you want me to give you like a set of quantum numbers that like
Please give me possible ones.
Okay, possible ones. All right. 3, 0,
0,
0,
okay.
negative half.
Negative half, right? So the first thing that I'll look at personally is the L, because the L will tell me where I'm looking at. So since it's 0, we're going to be looking on the left side. Now we'll look at what row we're looking at. So here it says 3. So now we know that we're looking at the 3rd row. Let me change the color here. We're going to be looking at the 3rd row. So it's negative 1/2. So are we looking at sodium or magnesium?
Magnesium.
Magnesium, right? Because if it's on the right side, that's what negative 1/2 will be. You guys want to go over another example?
I had a question real quick.
What's up?
So I'm a little confused. So like you said, like the 0, 0 on the top, and then the negative 2 to 2, and then like it continues there. Are those the L numbers or?
Those are the M sub L numbers. So the negative 2, negative 1, 0, 1, 2, the negative 1, 0, 1, all those are the M sub L numbers. Let me write these in. So if it's green, that's the M sub L. If it's purple, that's the L. Yeah. Okay.
I
Do you
don't
guys?
understand how you figured out the green numbers though.
Okay.
You draw them the orbital diagram box.
Oh, okay. Yeah. Honestly, I haven't used that in like forever though. So for each of these, how I said earlier, how it goes from like L to negative L. So when L equals 0, you'll have a orbital. M sub L is designated for each of those orbitals that are in that L, which go from negative L to L. So for 0, it can only go from 0 to 0, which is 0. For 1, it can go from negative 1, 0, all the way to 1. So there will be 3. For 2, it'll go from negative 2 all the way to 2, and so on and so forth. So what I did is that for each column, I designated a certain electron for it. So those are the first 3 columns, which is all unpaired. And then for the downs, those are their own separate ones as well. So let's say we're looking at the second row. For the ones that are up, it's boron, carbon, nitrogen. And then for the ones that are down, it would be oxygen, fluorine, neon. And that's how I separated them.
I kind of want to add this. Remember, this is only applying to the its last shell, because remember, each element has all previous shells completely filled with electrons. This is just showing like what its last electron and its last shell or orbital looks
Yes.
like.
So this.
But also notice how each of these, they look similar to your subshell. So notice how you can only put 2 electrons on the 0, so that would be your S. Your 1 is equal to P, 2 is equal to D, and so forth. So 3 is your Fs.
So you use the valence electron to figure it out.
Exactly.
For quantum numbers, it's specifically the last electron. So that last electron in that last orbital of that last shell tells us everything about that electron, that element. So like you see how I put oxygen for this down electron? That's because that's the final electron for oxygen. For this one for fluorine, that's the last electron for fluorine. So they may have all these other electrons that are in it as well, but that last electron is what's important, which is why I circled it as so for each of these. Does it make sense?
Yeah, thank you.
Okay. So for quantum numbers, the way that I see it is like it's a GPS. It pinpoints exactly where on the periodic table we're looking at, because none of these elements will have the same last electron in their elemental form. So did you guys want to do another example of quantum numbers, or did you want to go back into the question sets?
The questions. But you did say, sorry, just to recap, you did say that when it's on the right, it's negative 1/2 and then left positive?
Yes.
Okay, thank you.
Hey Jerry, can you make Sophia a co-host again? For some reason, I took it away from her.
Oh, that's probably because she left. So for 10, we're looking at the values for N and L for the 4D subshell. So when we're looking at the D subshell, what do we say about the D subshell when it comes to N? Are we changing it or?
Doesn't it go up to the previous one?
Okay. So if we're looking at 4D, what row are we actually looking at?
3.
Four.
N would be 4 now.
Okay, so look at your periodic tables that are on your workbook real quick. Remember that the first row for the D subshell is 3, right? We all understand that?
So we're looking at row 5 if we're talking about 4D.
Perfect. Yes. So we'll be looking at row 5. So Alan, quick question.
Yep.
So do we apply that for this one? Because I always get it.
For which one are we looking at? Number 10, right?
Number 10, yeah.
What values of
Choosing an N value or an L value?
An N value.
For 4, so for the 4D, it would technically be
5, right? Because N minus
yeah.
1 gives you.
Yeah. So it would technically be, so from anything that, so for N, so anything that's past 4 technically. Well, technically 3, right? Because if you do your N for your L being N minus 1, so you had up to 2, because technically
It's because 4D means that we're looking at the 5th row. That's why I'm thinking that N's 5.
Yeah. So N is always going to be the row of the periodic table that you're on. So you just first thing you're gonna have to do
Okay.
4D. So that's gonna be right here, right? And you're gonna count how many rows down that is. So that's 5. So then your
N will equal 5. Yeah. And then L. Well, when we're looking at D, what's the number for L? Zero, 1, 2, or 3?
2.
2, right? Perfect. So that's it for 10. Now,
Dr. Alexander put the N was 4. Because is it not the shell? And it's the 4th shell.
4. That's why I don't like that. Because technically, if there is a 4D subshell, there would be a 5th shell. But I guess what he's trying to say is that specific subshell, which is in the 4th energy level.
Because remember, when you're, well, in normal circumstances, right? When you're giving the quantum numbers, you're referring to a specific electron. So for the most part, when you're doing quantum numbers, the first thing you're going to do is do your electron configuration. And then depending on what electron it's asking you for, that's where you're going to pick all of your numbers.
So complicated. No, I think it's just because he specifically is talking about this subshell that we'll just be looking at this. But whenever you're looking at an element as a whole, it won't work like this. This is only because we're looking at this specific subshell, which is 4D. And the way that that would work is it's N, D, N, S, etc. So that's what N would be.
It's a lot of complexity, and then it gets into like quantum mechanics as well. So.
Oh, don't bring that up. But yeah,
but you guys
he
are
just
there
weirded
yet, so
it
you don't have
weird.
to worry about it.
He just weirded it weird, yeah. So, did you have a question?
Yeah, I'm sorry. Can you explain it one more time? Like, L is 2, because I thought it's N minus 1. Yeah, I don't know. I'm just confused on that.
Okay, so for L can be anything that is less than N. So, as long as it's less than N, it could be L, all the way to 0. And the way that we show this is that the highest that L can be is N minus 1, because it needs to be a whole number. So the highest L can be is N minus 1, but L can also be N minus 2, N minus 3, N minus 4, etc., etc. Does it make sense?
Okay, and so for this one, N would be 4, right, and not 5? Or that kind of confuses me too. So N is 4 then?
Yes. So in this specific instance, specifically only for this question, N will be 4. Any other time. Okay, so here it's specifically 4 because it says that we're talking about the 4th subshell. If we're talking about a specific element, it would be 5.
Okay.
Also, going on to why L is equaling to 2 specifically is, if you remember, the L is telling you, the number tells you the type of subshell, where 0 is your S shells, 1 is P, 2 is D. So it's specifically the 4D subshell. Since we're in the D subshell, then L has to equal to 2, since we're specifically looking at that.
Oh, I can't write that. Well, technically it goes past F, but we don't talk about that. So 11, what are the allowable values of the spin quantum numbers S and M sub? That's supposed to be M sub L. I'm pretty sure. What are the allowable values of the spin quantum numbers? Yeah, I'm pretty sure it's M sub L. So based off of what we have for L, what can M sub L be? We kind of just said it earlier. Question 9, you know?
Okay, I need to say this because it's my pet peeve. So remember, for quantum numbers, you can only give 4 numbers total, right? But M sub L has options. So specifically for this problem, what are the options for M sub L?
Sophia, Alan, I need to talk to you guys after this. So what can M sub L be?
I'm confused because is the question about
Oh,
the F?
it's a follow-up of 10. It's a follow-up of 10. Sorry.
Oh.
So based off of L equaling 2 from 10, what should the M sub L be for 11?
-2 to 2.
-2 to 2, right? So -2, -1, 0, 1, 2. And then M sub S, what can M sub S be?
-half and half.
Perfect, -1/2 and +1/2. So the negative and the +1/2, you won't know until you know exactly where it is, wherever on the periodic table, or like what element it is. So number 12, state Paulie's exclusion principle. We've kind of talked about it already, but what's the most important thing about Paulie's exclusion principle? No two elements have the same what?
Well, not elements specifically, but electrons within an atom.
No. That's, well, I was getting to that, but yeah. Honestly, for this one, as long as you understand like how it pertains to quantum numbers and electron configuration, you're good.
Think of it this way. What are we working with? Pigs, horses, cows, unicorns?
And quantum numbers?
Quantum numbers, yeah.
Okay, and what do those quantum numbers tell us? They tell us the location of what?
Elements.
Wait. The electron. What electron?
The valence electron?
I'll take it. So that last electron, right? So can nitrogen and oxygen have the same location for their last electron? Can they have the same amount? Elementally speaking.
No.
No, right? So that's what Pauli's exclusion principle literally is. No two Oh, dang it, I tore that. No two elements can have the same last electron, basically.
And if you want to be even more specific about that, it's like no two electrons within the atom have the exact same quantum numbers. There's always going to be like one of their values is going to be different from the other, no matter how similar they seem.
Right.
And that's
right.
because no two electrons can take up the same space. Think about it. You and your mom can't exist at the exact same spot on Earth at the exact same time. So
don't
same
bring up
idea with
Schrodinger like
electrons.
that. Yeah. Oh, you're like saying so many taboos in my class right now. Anyways, electron configuration. So for hydrogen, how many electrons do we have for hydrogen? Where is it on the periodic table?
1, so it's 1s. 1.
Beautiful, 1s. And since it has that one electron that's in that 1s, we'll put 1s, 1. That's a 1, not a p. I don't know what the heck that's supposed to look like. So nitrogen, what would that one be? Where is it? What does it reach all the way to? What subshell?
P.
Okay, so we know it's P. And what row is it?
The second row.
Okay. And how far is it into the P subshell? Counting from left to right.
3.
3. Okay, so 2p, 3. And then we can just work our way backwards. So before P, what is it?
2s2.
2s2, because you got to fill that one. And then before that, we have the first, which is 1s2. Make sense?
Yes.
Perfect. All right. So moving forward, neon. This one I don't think really needs explanation since it's pretty much the same. What about magnesium? Actually, do you guys want to continue with the electron configuration or go to the next question set? Because we have 10 minutes.
Next question.
Sounds great. Let's get a move on.
Do you want me to take over, Jerry?
Go for it. I've been talking too much.
I have a question. So I know we haven't started with this one, but for the Stokes study set, well, you know how when it's like 2+, then that means you lose electrons, and then when it's minus, you gain. So if we're in the 3D block, right? Like if it's an element on the 3D, on the D block, and we have to like lose electrons, do we lose the electrons from that 3D block, or do we lose them from like the last one? Like, you know what I mean?
That's a perfect question, and I love that question. You will be taking it from the highest energy level. So if it has a 4s or a 5s or whatever, you'll take from that first. And that's actually why transition oh, my bad.
No, perfect. It's because when I was looking at my work and the answers, I noticed it, but I didn't know from where we were supposed to take electrons from.
No, yeah, that's exactly it. That's actually why transition metals have multiple charges, because they can pull from, like for iron, how it has a 2+ charge and a 3+ charge. That's because it takes 2 from its 4s, but it can also take 1 from its 3d since it's 3d6 and stuff like that. But for electron configuration for ions, basically what you're trying to do is see what element those ions are the same as. So for aluminum ion, what does it have the same amount of electrons as? So 13 minus 3 gives us 10. And that's what isoelectric is. And that's how this be.
Yeah, because remember the elements are trying to live the noble gas life. So for the most part, or actually always, the ions are trying to be a noble gas. So whatever noble gas you're trying to be, that's the electron configuration you're looking for. So do you guys want to try some of these ionic electron configurations?
I'm so sorry, can you repeat that?
Yeah, I don't know how much of that, but like the elements are trying to be, the ions specifically are trying to be like noble gases, right? So when you're asked for the electron configuration of an ion, right? One of the things you can do is you can determine which noble gas you're trying to be, right? So Jerry mentioned the aluminum ion. So 13 minus 3, right, is 10. So which element has an atomic number of 10?
Neon.
Neon, right? And that's a noble gas. So then when you're asked for the electron configuration of the aluminum 3+ ion, you can think of it as you're writing the electron configuration for neon. And that way you can like double check your answer.
Oh, okay. Thank you.
Mm-hmm. So do you guys want to go over some of these ion electron configurations, or do you want to skip into the next problems?
Can we do like the ones from that have like the 4S and for like 3D block stuff? Like M2 and from the first question.
Okay, first question.
Like
oh, like
M1.
manganese.
Uh-huh. Yes.
Manganese. Okay, sure. So first off, let's start with neutral manganese. What would be the electron configuration for neutral manganese? So just Mn.
It would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. And then we would do 3d4. No, 1, 2, 3, 4, 5. 5.
3d5, right? So I don't know if you guys noticed, but she said 4s2 first and then 3d5, and I wrote it the other way. Dr. Alexander went over this in lecture, and he told you about it, and he asked you to please do him a favor and always write the last energy level at the end. So that's probably where that confusion about where to take the electrons from is coming from, is you guys need to remember that you need to write your electron configuration in order of increasing energy. So the 3D orbital is going to have less energy than the 4s orbital. So you need to put your 3D orbital before your 4s orbital. Does that make sense? So the way that I have it here, basically. And then when you're asked for the ion, so you start with the neutral form, right? And then now it asks us for the 2+ configuration, right? So if we have a 2+ charge, how many electrons are we losing? Anybody?
You're losing 2 electrons.
We're losing 2 electrons, right? So where should we take away those electrons from? Can we take them from here?
No.
No, right? So where do we need to take them out of?
I think the 4.
The 4, right? We're going to take their electrons from our highest energy level, the one that's furthest away from the nucleus. So that's going to be our 4s. So, you know, basically what you're going to do is, because remember these exponents represent number of electrons, right? So you're going to take 2 electrons from this shell. So 2 minus 2 is 0, right? So basically you're just going to get rid of this part of your electron configuration. So then your electron configuration for manganese 2+ is going to be the same thing, or whatever's left, I should say, right? So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Yes? And then for manganese 3+, I'm going to backtrack real quick. So let's say we're back to the neutral, right? And now we're going to take away how many electrons if we have a +3 charge?
3 electrons.
3 electrons, right? So we already said, I mean, you can do 3 minus 2, but then you're still going to be missing. So you can take away these 2 electrons, right? So then we still have to take away 1 electron. So where can we take it away from?
Probably from that D5.
Yeah, the 3D, right? Because that's the next highest orbital. So then this turns into 3D4, right? Because now we only have 4 electrons in that shell. So then our electron configuration for manganese 3+ is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d4. Does that make sense to everybody?
Can I add something real quick?
Yeah.
Just another, I guess, like friendly little thing. Yeah, just real quick. When you see the numbers that are in front of the letters, so like 1s2, 2s2, 2p6, that 2, 2, 6, 2, 6, etc. When you add those up, they should equal the number of electrons you should have in that element. So like for this base one where it's 2, 2, 6, 2, 6, 5, 2, I'm looking at the electrons for each one. When adding those up, it should equal 25. And that's how it should be for each of them.
Yeah, because remember the exponents represents how many electrons you have in each suborbital. So if you add up all of your exponents, it should tell you how many electrons total you have. So the total number of electrons that your ion or whatever element you're working with should equal all of your exponents added together. Everybody good with this? Cool. I'm gonna clear the whiteboard. That's not the clear button. Okay. Okay. Let's see. Both nitrogen and oxygen atoms use 1s, 2s, and 2p subshells for electrons in their atoms. Which one of the following is true? It says A, the energies of the 1s, 2s, and 2p subshells are higher in an oxygen atom than in the respective energies of these subshells in a nitrogen atom, or they're lower in oxygen than in nitrogen, or they're the same energy in oxygen as in nitrogen. So which is it? So this one is saying the subshells in oxygen are higher in energy than in nitrogen. This one is saying that the subshells in oxygen are less than the subshells in nitrogen. And this last one is saying that the subshells in oxygen have the same energy as the subshells in nitrogen. They're the exact same subshells.
It's D.
B? Does anybody disagree? Anybody agree? Gonna take that awkward silence as in everybody agrees. Yes? I'm not sure why though. Jerry, is that the answer?
It's the answer. It's because since nitrogen has 1 more electron in the 2p shell, that 2p requires more energy than oxygen's 2p.
Okay, that makes sense.
Actually, oxygen has more electrons.
Was it the other way around?
Yeah, oxygen has more electrons.
Yeah, it was. Okay, it was the other way around.
All okay, right. So then it's not B, it's A, right? Right? Or is it B? Wait, I'm confused.
No, it's B. The answer is B.
And the answer is B because
Care to elaborate,
has
Alan?
more electrons?
No, so because like that was the other way around, but no, okay, so because oxygen, so remember let's see here, look real quick. Respective subshell energy. Okay. So since there's oxygen has a quote unquote more complete subshell than nitrogen, it requires less energy in order to maintain it. Because nitrogen is quote unquote less stable than oxygen, for example, since it has less filled. Because remember, orbital shells, they prefer to be either half filled or completely filled.
Does that make sense to everybody? Cool. Gonna take that awkward silence as a yes. Okay, so now we're doing decreasing diameters, or you can think of it as decreasing atomic radius, right? Similar measurement. So which of these has the largest atomic radius?
Just real quick, if you guys need to go, it is 6:30, so the review is technically over.
Oh yeah, I guess we'll make this the last question then, unless somebody wants to go over something else. Oh yeah, maybe we should make it all available. What else is left?
Yeah, can we go over those? Because I really don't get those.
Sure. Let's go over number 5, or do you want to go over 6 and 7? Which one specifically? Or all of them?
Well, for sure, at least like 6.
Okay, so I think Jerry is the most qualified to explain this to you guys theoretically. But all I'm gonna say on my end is from the PowerPoints that he sent you is slides that are named 6.7. I don't remember what slide specifically it's on, but it's basically he gave you the drawings and you're just remembering it basically. But I think Jerry is the most qualified to explain why it's that way for you guys.
I mean, honestly, I'm barely learning this myself, but I understand it a little bit.
Yeah, this is a very advanced topic.
Yeah, oh yeah,
Sorry.
I'm learning this in PChem.
Yeah, so Dr. Alexander just likes to make you guys aware of this. So don't be alarmed if you don't understand it, because I mean, this is like physical chemistry, which is like a junior level class. So yeah.
But it's most likely that he'll just like show us a picture and tell us to identify it, right?
Oh yeah, 100%. If it's on your exam, it's going to be the exact same question that was in the study guide. So I hate to be this person, but just memorize it.
Memorize the answer. Just memorize the answer. I don't even remember it being on the exam, but just in case, I would legitimately memorize the answer. Because it's going to look just like that.
Gen Chem with Dr. Alexander, I remember number 6 being on the exam. But I don't know if he's...
I have the answer sheet open.
Oh, I know what it is. I can draw it. Okay, so it's going to be... This is the XZ plane, right? So this is X, this is Z. And then your cosine theta function of this is going to be a sphere this way and a sphere that way. And I'm about 97% sure this is the positive end and this is the negative end. And that's the max, I think. Right, Alan?
Wait, does it show a positive or a negative on it?
I think so.
Because if it doesn't, then I wouldn't.
No, it does. It does. The top is positive, the bottom is negative.
Okay, but yeah, that should be it. Because that's specifically for PZ. That's how that be.
Yeah. Wow, look at me remembering this. This is from like way back in the day. Okay, anyway. And then number 7 is
I
similar.
can draw that one, I think.
Oh, you can do that one? Okay, go for it.
Well, it's the same thing except that it's sideways.
Yeah. Oh, I erased it. So I'll draw it. It looks like this. And then this is X, this is Y. And then again, you have little, oops, pretend that's connected. Like this. And then I think this side is positive and this side is negative. Right on?
Yeah, it's like that. Mm-hmm.
Anyway, now I'm celebrating that I still remember things. And then the contour diagram.
Oh, for that
spicy.
one?
So
well,
I'll let you guys take over. I don't remember that one.
For 5A, like all you're doing is you're figuring out the R at when it's at its maximum. So when it's at its highest, which is, oh, let me draw.
I got you.
Yeah, when it's at its highest, so it should be 2. And then when it's at 50% that, so around 0.5. So there will be 2 values, which is 0.5 and 5.5. That should be it. Make sense?
How do you see where it's 50%? Sorry.
All right, so we know that the maximum is 0.3, so that means that half of that will be 0.15. So like divided by 2. And then, well, 0.15 is halfway between 0.1 and 0.2. So you can do a rough estimate sketch as seen here with the dashed line, and that will give you roughly 0.5 and 5.5.
So this question is literally just asking you to interpret the graph, basically. Welcome to algebra. Just kidding. This is chemistry.
Sorry, I over-exaggerated a little bit on 6 and 7 because he gives it to you. Any questions?
One last question.
What's up?
For number 10, it's because I forgot what the definition for paramagnetic means.
All right, so paramagnetic and diamagnetic is the following. So for paramagnetic, that means that it has a net charge, or it has a net amount of unpaired electrons. So all of them, except for neon, should be paramagnetic. And all noble gases will be diamagnetic. Or like all of the elements that are on the last column for each subshell will be diamagnetic. So the second column, the column with zinc in it, the column with helium in it,
like in case you forget and ask you for an element or like its ion, you can draw its last valence shell, like the orbital diagram box, by pairing, drawing the electrons, and you can see how,
with the arrows.
Yeah, exactly, with the arrows, and you can see how the last electron is either paired or unpaired, or whether all electrons are paired or not.
Okay, thank you so much.
Any other last questions?
So does that mean that the copper isn't paramagnetic, it's diamagnetic, or?
Well, let's draw the box orbital for copper. How about that?
Why did it have to be copper of all elements?
Because of question 10. Because in question 10, for the copper 2+, or the magnet, whatever it's called, it says which one's more paramagnetic.
Yeah.
So how do you know if it's more or less?
Well, if it's more paramagnetic, it'll have more unpaired electrons. So if you have, like, for example, let's try it. 1, 2, 3, 4, 5. For copper, what is it? Copper 2+?
Oh, copper 2+ and manganese 2+.
So you're gonna have copper 2+ is gonna have 9 D electrons, right?
You can make this a lot simpler.
Oh, go for it.
So they're both in the same row at the same area. So manganese, is it on the left side or the right side? Is it a +1/2 or a -1/2 for starters?
+1/2.
It's a +1/2, right? So that means that it's already paramagnetic. Copper, is that one a +1/2 or a -1/2?
Minus.
So that one's a lot more likely to be diamagnetic. So just from that alone, you can already tell that manganese will be more paramagnetic just due to the fact that it doesn't have any paired electrons in the first place. Well, in that last subshell. Does it help?
Yeah,
Coolio.
thank you.
Great. Any other questions? Oh, could you stop recording?
Oh, yeah.